Hi, and welcome to Talking Tech. I'm your host, Alejandro Hoyos, and I am very excited as we're going to be talking about Intel's latest processor, Meteor Lake. We have gone from a monolithic die to a complete disaggregated multi-tile, which is Meteor Lake. We're going to be interviewing different architects and engineers that are going to take us through different tiles of Meteor Lake, which are the I/O tile, graphics tile, compute tile, and the SoC tile. We also had the opportunity to travel all the way to Malaysia to learn more about Meteor Lake's packaging and tour the different facilities that cover assembly and testing. So now we have this new architecture, the new name that we call it. We call it the 3D Performance Hybrid Architecture. Can you tell us a little bit more about what this is?
We have had P cores and E cores, right? We had that since Alder Lake timeframe. We still have that on Meteor Lake timeframe as well. So our compute tile that we have on Meteor Lake, that has P cores which are designed for high performance for ST limited threading cases such as gaming, content creation. We deliver on that. Then we have our E cores on the compute tile, which is basically there to deliver multi-threaded performance under given power envelope. And then with Meteor Lake, we added this SOC the SoC tile that we have. And on SoC tile, we added E-cores as well. And those E-cores really, the objective of that is providing energy efficiency to that design point.
And what we're doing there is having the ability to have separate E-cores on the SoC tile in this thing we call the low power island. And the low power island is not just E-cores, but consists of key IPs like the media, the camera, the display, and other IPs to allow us to do a wide range of workloads in low power mode. And what's great about this is while the low power island is on, we can turn off the main compute tile. So as part of our disaggregation architecture that we did with Meteor Lake, we were able to actually break those tiles up and have the ability to turn some of the tiles off.
So let's say if you have, low usage activity going on that is not scaling, it doesn't need as many cores or anything. We can run them on the SoC tile and keep the compute tile powered down. And this helps us get power benefits. But when we need that high demand, high performance work, we have our compute complex, we run things on that, and we deliver on performance as well.
So we have the low power islands, the cores that are in the SoC. Mm-hmm. Then we have the E-cores and the P-cores that are on the tile compute.
Yes.
And so all those three is what we call the 3D
performance architecture.
So for Meteor Lake, there's a few things that we really focus on there. The first is the DLVRs. DLVRs we integrated into Meteor Lake in order for us to allow fine power control of each of the IPs. It allows us to control individual tiles, but it allows us to go to the IP layers itself to control the performance of that IP, set the right optimization point based on the workload itself. The other thing we did for power management, we optimized on the fabrics itself. We wanted the fabrics to be very dynamic based on the workload and just the performance. With the disaggregation, we increased the size of our fabrics to have better performance. We have some additional traffic going between the tiles themselves, but we also focused on the power management to do this. The best way to think of this is if a workload demands lots of bandwidth between one or two tiles or certain things we can optimize the fabrics between those tiles while the other tiles can be lower power mode. And so this allows us to have that flexibility to adjust our fabrics to address the bandwidth and the speeds and the performance we need based on the workloads that are there. All this work is now tied back to the software, so Intel Thread Director can have the ability to schedule the right thread and the right workload and the right core at the right time, and it allows us to turn the other tiles off. And so that software and tying it back to the overall system software has been very important to do that. And the Thread Director allows us to give hints to the OS to actually move the threads back and forth between the different cores and do the optimization points that are there.
Okay, let's talk about the improvements I've done to the Thread Director.
Yeah, definitely. So, this is kind of our continuous attempt to help improve hints that we provide to operating system in assisting them to come up with the right placement decision on our hybrid architecture. In Meteor Lake, we have our SoC tile, right? That's new. Mm-hmm. So there is SoC tile specific algorithms that are part of our enhanced power management that got incorporated into Thread Director to kind of reflect to OS that, hey, now is the time to keep the work on the SoC tile, or now is the time to move the work from SoC tile, right? So, just to give an example on that, right? Let's say that I'm running some CPU intensive task on my computer Meteor Lake system, right? Mm-hmm. I have 4 threads and I keep my P cores active because I really need that performance back. Now if some audio playback or video playback started, since I have my compute complex up, there's no point in waking the SoC complex, even though the work could have fit in there. Then we recommend to OS that use the E-cores on the compute tile to do that low usage work, right? But once my foreground high usage, if I'm running a game or content creation, that is finished, and I only have that low usage activity, then thread director reflects back to OS saying that, hey, the efficiency ordering has changed. SOC tile is more efficient, so the work can move there, and we can power down the compute tile. So all of this gets communicated to OS from hardware in terms of this thread director table that we provide.
That's pretty cool. That's pretty amazing. And it's all focused on, try to save that power and get you that extra 3 hours of work in the plane.
You get extra time, and also you don't sacrifice on performance, right? Because that's one of the other objectives we have.
We've really been focused on having, from the very beginning, it's focused on having the most power efficient SoC ever with Meteor Lake. And we really set out to achieve that. It was a combination of the IPs that we did, the disaggregation, but also the thread director. It comes together there. And the partnerships with OS. Microsoft's been a great partner. We've been working with them very closely in order to have this really work and really be seamless. And we're really excited about this, having this full range of giving that great performance and great battery life.
I mean, think about it as a first step in our journey for disaggregation, right? We are going to double down on this. We have more products and architectures coming down this pipe. And then as we put more Meteor Lakes out there, get feedback, use that to improve our next disaggregation step that we have coming up.
You don't have to choose anymore. In the past, maybe we would focus highly on performance, or you get battery life modes. With Meteor Lake, you get the best of both worlds. You get great performance when you need it, based dynamically on the application and workloads, but at the same time, you get great battery life. It's all done under the hood. Software and optimizations there is dynamically done to give you that great. So it's no longer a trade-off, it's that you get best of both worlds.
It's a multi-tile processor. How is that different from previous processors?
Great question. So the way I would say this is that, if we take a step back and look at what we have done for Tiger Lake or any other processors we have, it was all monolithic, meaning just one single die.
Meteor Lake is actually a combination of multiple dies, right? Not just the SoC, right?
So Meteor Lake, as we know, was the first time that we did die-level disaggregation, right? So we had multiple dielets, the SoC dielet, the compute dielet, the graphics dielet, and the IO expander or IOE dielet.
And of course, we also have a dedicated tile for the base die. So these are the tiles that we have for the overall Meteor Lake SoC in general.
So the concept of having multiple dies within a single package isn't new, but Meteor Lake is revolutionary with the notion that we're going with a Foveros 3D construction.
So what happens is that we have all these tiles or the dielets on the top, and there's a base die that is sitting, that is where you have the connection. And what will happen is that, let's say compute wants to talk to the SoC, compute will go down, go through this base die, come up, and will talk to the SoC.
It's first time we're doing this multi-tile design. And to me, it sets the groundwork for our future generation products to be able to mix and match and get the best out of process technology as well as performance when we need them.
The big thing here is when we disaggregated, the idea was you get the best design with the match to the best process, and hence you can keep moving things around.
If compute is very important for you, you go replace the compute with a next generation compute on a next generation process, and you're only changing the component that is really important for you.
Usually when you have all these various IPs revving, including a new IP like the VPU for the AI accelerator, you would count on the fabric being pretty stable. But this time around, given in the previous generation, which was Tiger Lake, right, we had maxed out the bandwidth capabilities of the previous fabric, which was PSF.
This fabric is responsible for getting the traffic from the memory in and out, right, into these IOs as well.
We needed to create a new high-performance fabric. So part of the Meteor Lake architecture is the creation of a new network-on-a-chip fabric, NOC fabric. We have our NOC, and it's a cache-coherent fabric. And then the devices that are attached to that, we have our two tiles, compute tile and our graphics tile. Those are attached to it. And then inside the SoC, we have media, display, imaging, our new NPU, and then our low-power SoC E-cores. Those are the main devices that are on it. And then attached to that, we have the memory controller, and we have like power management controller. And then we also have a bridge to our IO fabric. So it's our NOC fabric. We have two main fabrics, our NOC fabric and then an IO fabric.
In Tiger Lake architecture, okay, think about this like we have one highway, okay? That highway was getting shared with like IPU and the VPU and the display. So if there is a jam, then some other IPs or the agent IPs that actually had to wait. In our case, the way I would say this is that Meteor Lake is the true SoC that actually had multiple highways for different agents. Meaning that, for example, if IPU wants to talk to the memory, you don't necessarily have to wait for the others. You actually have your own channel and go to the memory. If you have display, which needs a higher prioritization, it will go to its memory link directly.
Is it a one-way street or is it a two-way
It's both ways. And within each way, there is multiple data types that have dedicated resources. And then on the fly, you could have prioritization.
It was very challenging, right? I mean, a lot of work, a lot of architecture innovation went in. The power management was revamped. Every IP had its own power management agent, which talked to the P unit.
The intent had always been, how can we be the most power efficient? How can we bring the most low power integrated platform features, right? While not taking up the power from CPU.
We are giving the tremendous amount of flexibility to the IPs so that they can talk to memory directly.
So you can have certain power-hungry, high-performance die on a really advanced technology. And you can mix and match to what that product eventually needs.
Strategically, what we figured out is not all IPs in the entire Meteor Lake need to be on the latest cutting-edge projects. There is an optimization that you could be done across power, performance, cost vectors, and that gives us the ability to split the die into multiple tiles and tailor the IP for the process node that's best suited for it.
The thing what we are looking for Meteor Lake was that we are not looking for a patched solution, but we are looking for a solution that is scalable. Meaning that today I have, let's say, 3 agent IPs, but tomorrow if I have like 3 more, will I have a design that can support this, or do I need to redesign this? And based on that, keeping that definition in mind, so we have architected in such a way that our fabric is scalable, meaning that if you want to add like 2 more agent IPs, I don't have to respin this. I already have the mechanism to just do a plug and play and go.
Meteor Lake gave us a unique opportunity for some of the dies, like IOE in our case, right, to be able to start from scratch, right? New development, new infrastructure, new validation collateral, a new way of doing things. So Meteor Lake was a combination of picking and choosing the right combination of, which ones do we want to keep, which ones do we want to throw away, right? Needed to be intelligent about not just everything from scratch, but more conscious and more strategic about, which pieces do we want to redo versus build from scratch or fix or things like that. So.
When it comes to clock domains, clocks sometimes could be finicky. How do you guys overcome that issue of jitter and clock trees and delays? And
For Foveros, to go across die to die, we use a forwarded clock architecture.
Okay,
it's
that makes
a forwarded
sense.
clock architecture for our audience out there that understands what forwarded clock architecture. If they don't, I'll give you just a little primer.
Yes,
a little primer, and that the clock is sent along with the data across the die to die.
That high frequency design, verification, clock design, right? Replication of clocks from one die to the other, handshake of signals, right? And FIFO design and all that stuff, right? Was very, very interesting, very challenging, and one of the, I think, very rewarding elements of Meteor Lake, for me at least, which I worked on.
What have been some of the greatest challenges you've run into?
In Meteor Lake?
Yeah, in Meteor Lake.
Okay, so as we started Meteor Lake journey, we got hit by this pandemic. Okay, no one knew as to how we'd respond to this pandemic. While the pandemic was happening, we are going full speed ahead with the Meteor Lake execution. But guess what? At the end of the day, this team rose to the occasion and we delivered this in style.
Many new collaborations, new teams coming together, and we have to figure out a way to work together as a team, collaborate, and just make it happen.
Since I spent a lot of time in physical design, the scale of the challenge is just enormous. We had great collaboration with PESG. We had great collaboration with the industry EDA vendors, being able to work with them on a daily basis to solve, the humongous challenges, because taking a leap of faith and improving productivity by 5x in a generation is extremely challenging, and when you accomplish it, it's extremely rewarding.
And I think it was a learning experience for everybody, right? The use cases were different, like VPU. I mean, now it's all AI, but even now we don't understand all the use cases well, right? So 3 years back, it was this thing called VPU. Does it really need to have this real estate devoted to it? What does it mean for traffic patterns? Who should get priority over what? Who gets the higher metal resources, if you will? We have an awesome team, and that, really came through in Meteor Lake.
Meteor Lake is truly big. The disaggregation has changed and is going to change the way we are delivering. We've learned a lot in this. So we've become more agile. We've become more adaptive.
I think Meteor Lake paves way for the new architecture, right? New foundation of how client SoCs are built, and it paves the future for us to be more agile, right? And hopefully our execution cycles in the back end will improve from here because of the whole architecture which we have.
I'm super proud of Meteor Lake. I really am. It was phenomenal to see this new revolutionary architecture, and then all of Intel gathered around to work together to build it.
Simplistically, I would say that, hey, go test it, get it, buy it, and enjoy it.
Right now, we're in the middle of our journey of 5 nodes in 4 years. Right? When Pat came back 2.5 years ago, he put in place this plan for technology leadership catch-up. And that's the 5 nodes in 4 years. So step 1 was Intel 7. Step 2 is Intel 4, and that's where we are today. So if you look at Intel 4, our goals were first area scaling. So if you look at our standard cell library and you compare it to the Intel 7 node, we're able to achieve 50% area scaling, or 2x area scaling, however you want to describe it. That was, the continuation of Bohr's law. Second goal of Intel 4 was power efficiency. Right? We want to deliver a lot of performance, but it needs to be efficient performance. Some of that we get from the scaling, and a lot of that we get from the transistor improvements that we implement as well. And our goal really is to take most advantage of power efficiency. When we drop a gate contact, prior to 10 nanometer, you would never put it on top of a gate. It was always off the gate, and then you'd use the conductivity of the gate metal to get to the transistor. Starting on 10, we dropped it on top of the gate. And that allows that, because we don't have to drop the contact so far away, we can achieve better scaling.
So it's like you're reducing your area, right? Because
yes.
Now you have to put it outside, now it's directly on top, so it's less area. So
yeah, exactly. It's, a contact was sitting out here. Here's the gate, contact sitting out here, and then I can drop it right on top of it. So then I can, I chop the cell at the edge now. We also were able to pitch scale both the fins and the gates. EUV lithography was a big part of that. EUV lithography really allowed us to reduce some of the complexity that had grown over the years because we didn't have lithography capability of the resolution that we needed. We've been able to reduce complexity, and reducing complexity allowed us to achieve better yields. It's allowing us to run the fab faster. The metal stack is 18 metal layers. Now we have a 0 metal layer, and then we have metal 1 through 15, and then we have these giant metal distribution layers up at the top. So it's 18 tall. You're also challenged by electromigration, right? Electromigration is when you're putting, voltage or power on a wire. Sometimes that metal wants to move. And metal moving is not a good thing. Right? No. We developed what we called enhanced copper.
By implementing this new type of wire connection, you have also reduced the RC or the impedance on it, so making it.
Yes. Resistivity on those lower metal layers. If you compare resistivity or the conductivity improvements that we have in metal 0, metal 1 compared to Intel 7, it's a significant improvement. 5 nodes in 4 years. So Intel 4 is step number 2. and we're in production today. Step number 3 is Intel 3, and Intel 3 will build upon Intel 4. It'll offer denser libraries for scaling. It'll provide additional performance opportunities. Intel 3 is a node that we will use for a very long time for both internal and Intel Foundry products. So it's pretty exciting. Yeah. Step 2 done, 3 to go.
Foveros is what we call 3D advanced packaging. And by 3D, it means we're stacking die on top of, or silicon on top of other pieces of silicon. I think one thing that Foveros is kind of a first versus the like some of the other 3D packaging in the industry is that we do have the capability to stack 2 active die on top of each other. And we can also stack a active die on top of what we call a passive die. On Meteor Lake, for example, we have multiple top die, and we put them on a single base die, and that base die serves mainly to interconnect all of those die. So we could take all the die, instead of building them on one large die, we break them into smaller functions, and then we connect them with packaging. Traditionally, we do what we call organic flip chip packaging, where we take a monolithic die and put it on a substrate, and then on like Raptor Lake and Alder Lake, going all the way back to Haswell, we put the platform controller hub, or PCH, on the package, and we connected those together with what we call on-package I/O. And for example, those connections between the die and substrate are like 100 microns apart. We call the pitch, right? When we go to Foveros, those connections between the die and the wafer, they're at 36 microns. Since we're talking in area, it's about an 8x increase in the amount of interconnects that we can get per millimeter. So, you need that amount of signaling between the 2 die. Also, Foveros, it gives, the characteristics in the base die. It allows those signals to be carried at very high bandwidth and very low power, and as we said earlier, very low latency. So with the technology, you get the electrical characteristics you want, and that allows you to then partition into many different tiles.
So Foveros, if I understood correctly, you can correct me if I'm wrong, is we have this base wafer in which we have other tiles that come on top of it. So can you tell us a little bit more about that and how is it assembled?
Sure, that's exactly right. We actually start with all of them in wafer form. We have a base wafer, and then we have all the top tiles come to us in wafers. Some from internal, like our compute die on Intel 4, and then the other die that come from us from external foundry. We bring them in. All the top die we take through what we call die prep or singulation. So we'll cut up the die, singulate the die, and then we'll send them to sort.
My role as a factory manager, I take care of the entire factory operation, managing all the operation indicators to ensure operation excellence. At the same time, to ensure that we're meeting the cost target, as well as ensure all new product introduction and release on time. Penang assembly task is the backend processes to assemble the die into the packages, as well as to test the unit before finally shipped to customer.
We actually improve what we call known good die. So you get, something like a 3 to 4% improvement in known good die going into the package. So if you think about that, when you're putting 3 or 4 die together in a package, if you know that, say for example, they're 99% known good die because you tested them so well versus 95% known good die on wafer sort, which is still really good, but you just didn't have the same coverage, that multiplies out, and by the time you get to final class test, there's a 10% yield difference. After we sort them or singulated die test them, that's where we move to kind of the first step of the Foveros operations. This is what we call wafer assembly. This was, the major new capability that we had to put in. Obviously, we have to have tools and equipment and processes to take the top die and to stack them to the bottom die. So we do that. The bottom die or the base die is in wafer form when we do that. And the wafer assembly flow, it's kind of unique that it's a combination of both what we call like classic assembly processes and classic fab processes.
So particularly for Meteor Lake is a Foveros product. So where DMO, which is called Advanced Packaging Fab, will be doing the wafer level assembly in terms of connecting, attach 4 dies on top of the base die. So for ATM, we will receive the Foveros die, and we will do assembly, which is die attach or chip attach the Foveros die on the substrate and the packages.
We stack all the die onto the wafer, and then take it through the flow. We then singulate or chop up that particular die into what we call the die stacks or the Foveros stacks. After that, kind of circling back to that singulated die test, we do have the option to test them again. Since we are able to test at the die level, we are able to test at the die stack level. I think this is a big advantage. Sometimes there is a cost for adding a test step, so we have to use it judiciously. On Meteor Lake, we've been using it through development and sampling to make sure we have a healthy process. And then we'll evaluate how we use it in HVM or in high volume manufacturing, but it's still good as a quality monitor, making sure that the line is running well before we send the die to package assembly.
Once we do the attach, we'll go through all the assembly process step, whether it's epoxy, as well as the stiffener attach. Then we will go to test for completing tests before going through the finish operation to do a visual check and marking and before ship to customer.
I think the one thing about test, not necessarily just for Foveros, but again, we have world-class back-end test capabilities. All of our test platforms have been developed in-house over the past decade or longer. We can do this in a very manufacturable way where we're not adding a lot of test cost and test time, but still able to achieve that world-class DPM. And from there, we pack it and ship it. So, and that's what we're doing now. I mean, Meteor Lake, we finished all the qual samples. They are out the door this summer. Production materials in the line. The line's running pretty healthy. We're at our yield targets. Reliability, manufacturability targets. We're there or really, really close. So yeah, we're ready.
We are very proud to be part of this journey, to be able to enable the Meteor Lake Foveros packages and Intel 4 node, right? So that is, we are super proud and to be able to be part of this journey.
So the NPU, or the Neural Processing Unit, is completely new for Meteor Lake, and I am very eager to learn all about it because this is completely new for me. So please tell us a little bit more about it.
Sure, yeah. I guess I can use this diagram here to explain it. Well, first off, just to describe the motivation, the reason we have this is, we see the number of use cases for AI seems to be exploding, right? And a lot of these use cases we want to bring to the client, but these algorithms are actually running on the CPU, and you're kind of limited by the amount of, efficient compute you have. You can actually make the algorithm better, but then it's going to burn too much power. So when we bring the NPU, it's basically kind of a power efficient way to do AI. So you can take those algorithms, you can actually improve them. They'll take more compute, but we basically have, power efficient compute. So that's kind of the motivation to bring the NPU to the client. And the CPU is good for, very small workloads where you just want to, let's say the complexity of the workload isn't very high, you can actually execute it really fast. The GPU is good if you have, let's say, very large batch sizes. The GPU is good at kind of large batch size type of workloads, and maybe it doesn't run very long, so you're not worried about thermal constraints. The NPU is great for continuous workloads where you really want power efficiency, also batch size, one that has relatively higher complexity. That's really where it shines. Essentially, this is the NPU section, and then here's kind of the rest of the system. So we basically have kind of two components. One is, let's say, like the host interface and kind of the control for the NPU, and then the rest is kind of the compute portion. So the host interface portion communicates with the host that does all the kind of scheduling and memory management. The host interface also controls the scheduling on the device, power management, those kind of things. And then everything below here is kind of compute. Really the heart of the NPU is our fixed function compute block. We're calling it the inference pipeline. When you have a neural network, basically the majority of the compute kind of boils down to matrix multiplication. So we have what we're calling the MAC array in the inference pipeline block that does all that matrix multiplication. Actually, there's a lot of neural network operations. If we look at like OpenVINO, for example, there's like 160 plus kind of operators we have to support. Not all of them are matrix multiplication or activation functions. So we have a DSP. So this DSP is basically fully programmable. It can essentially support everything, but if you did matrix multiplication on it, it's just not nearly as fast as our fixed function hardware here. But if we have a lower compute operation, or we have some operation that just doesn't happen very often, we would run it on the DSP. the key things for neural network execution or neural network power are really how many times you read and write data, and then also how efficient your kind of matrix multiplication is. So through this, we can get a lot of data reuse. We have kind of internal register files, let's say, inside our Mac array where we can get a lot of data reuse that can help reduce the power consumption.
Okay, so we have covered the hardware side, but what about drivers and software side?
So there's kind of like two factors in the software. So the first is what is the driver model for the device, and that basically means how do we do the power management, how do we do the memory management, how does the security work? So we have a driver model called MCDM, which is the Microsoft Compute Driver Model. Then the other part is how does the developer program the device? What's the programming interface? What's the programming API? And there we've tried to have kind of a common API across the different hardware we support. So as GPU, CPU, or NPU, we're all supporting DirectML, WinML, OpenVINO, and Onyx Runtime. So we're trying to ease the developer experience. I mean, that's really the key for adoption.
For you as an architect, as a design engineer, how do you get, per se, predict the future? Do you have a little crystal ball? Like, how do you design for the future? How do you know what's coming up next?
Yeah, I mean, the exciting thing about the field is everything moves so fast. So, and this is all incremental. I think we have the right kind of base architecture. So we're making kind of, incremental tweaks. So let's say like a new paper comes out and there's a new kind of network architecture. We'll take that and then we kind of analyze it. We do like a simulation to see what's our performance. And then we look to see, like what's the bottleneck? What's taking the most amount of time, or maybe are we not having good enough efficiency? So then we go look to see, should we add some new fixed function hardware in the inference pipeline, or should we tweak, let's say, some of the way that we're processing data in the inference pipeline, or should we add new instructions in the Shave DSP? I mean, in Meteor Lake, we added a few new instructions based on new activation functions. There was new activation functions that were coming out. So we're like, okay, well, we want to make those faster. In our analysis, we showed that was a bottleneck. So we added new like vector instructions to the DSP, for example.
As you can see, Meteor Lake, from an architecture point of view and also from a product point of view, has a lot to offer. From new AI, new graphics, new process technology, a completely new type of architecture when we go from monolithic to disaggregated brings a lot of new features. Thank you for watching with us, and please stay tuned for more videos that will be coming your way.